Hi, everybody. I'm Matilda, and today I'm going to be talking about this recent project of ours in collaboration with Damian, Sanjay, Ethan, Kamran, and Kai. And the elevator pitch is as follows. So it's obvious to everyone in this audience that there are dualities in string theory, and they're fascinating because they let you map the high energy or strongly coupled behavior of one theory to the weakly coupled semi-classical description of another. Now, the fact that dualities are there from the top down is just kind of obvious. They're there. But we wanted to ask what are the possible imprints of dualities on low energy physics and whether or not there are bottom-up arguments to argue for their existence in the first place. So this, of course, fits in the swampland program. Now, we started with this observation that if you start with your naive moduli space that you get from compactifying, string theory, and you mod out by the action of the duality group, then you end up compactifying some of the dimensions in moduli space and sort of generating all of this non-trivial topology solely by modding out by the action of the duality group. Now, this motivated us to build this criterion on the geometry of moduli spaces, which should be at least be one of the imprints of dualities on low energy physics. The criterion is as follows. It says that the volume of moduli space as you go to an infinite distance limit shouldn't grow too fast. Namely, it shouldn't grow faster than it would if you had just like a flat moduli space. And this is interesting because, of course, we tested it in a whole bunch of examples of string theory, and it often seemed to go hand in hand with the fact that all of the particles, the spectrum of particles and charged objects, extended objects in your theory, have to transform in a semi-simple representation of the duality group. And in fact, in a very specific case, so 40 n equal to Calabi-Yau compactifications, you can prove this, that compactifiability implies this semi-simplicity. Beyond that, I just want to point out that, I mean, if you believe this, then it's powerful because you can then, exclude bad duality groups or say that they are incomplete, at least to some extent. So if you had 10-dimensional type 2B and instead of having the full SL2Z as a duality group, you only had the subgroup generated by the element T, that would mean that the axion would still have the shift symmetry, but the dilaton would be able to go all the way down to strong coupling. You wouldn't be capped off at zero. So if you look at the volume in the strong coupling limit, you see that it grows exponentially, which violates compactifiability. And on top of that, you see that the two-dimensional representation that you inherit from SL2Z is no longer semi-simple because there's this whole subspace of PQ charges for PQ fibrines and PQ strings that is completely invariant under the action of the duality group. So I told you we have this criterion that we tested in a whole bunch of string theoretic examples, but that's not enough, right? We need a bottom-up reason for why we think this is true. And for us, this bottom-up reason is going to be the fact that once you compactify all of your spatial dimensions to 1D, you should have a finite number of ground states. Why? Well, because then otherwise you would have an infinite amount of entropy in this one-dimensional system. You can also think of it as violating the baby universe hypothesis, which comes from the coercion conjecture, or there being an infinite number of instantons that tunnel between this infinite number of degenerate vacua, such that the amplitude to go from any one vacuum to the other goes to zero. So that's what we're basing the argument on. And the simple fact is that there are math theorems that state that if you have a metric on moduli space that violates compactifiability, that whose volume grows faster than that of flat space in the infinite distance limit, then you have an infinite number of ground states. You can just prove this. So there you go.